Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Learning Smooth Neural Functions via Lipschitz Regularizations, published at SIGGRAPH 2022. I'm happy to host Derek Liu, the first author of the paper, to talk about it. Hello, Derek, and welcome to the podcast.
Hello, everyone, and thank you, Isaac, for the invitation. It is really my honor to participate in this kind of great series of spreading knowledge. And also, most importantly, thank you, everyone, for kind of joining with us and then also listen to this paper.
Can you introduce yourself?
Yeah, so my name is Derek, and I'm my final year PhD student at the University of Toronto. And actually, after graduating, I will be joining Roblox Research as a research scientist.
And who are the co-authors of this paper?
Yeah, so this paper comes from the internship I did at NVIDIA. So paper is actually collaborates a bunch of great people at NVIDIA, including Francis Williams, Sanya Fiddler, and Lord Litany. And this paper also involves my advisor, Alec Jacobson.
Okay, so let's dive in. So in a TLDR kind of format, tell us, what is this paper about?
So this paper is actually very, very simple. We just try to propose a technique that you can help you to learn very smooth function parameterized by neural network. So for example, if you want to train some neural network and you want the result function to be smooth, and our approach is the solution to this problem.
So let's dive into the introduction. So what problem is this paper addressing?
So this paper is actually the key technical idea of this approach is to try to figure out a way to kind of measure how smooth your neural network is. And we propose a method to kind of encourage your solution to be very smooth. And the reason we want to work on this is there are many reasons that a person wants some smooth solution. For example, in graphics, a lot of cases when we want to do, for example, interpolating between two shapes, you want the interpolation to be something that's meaningful, to be something that's smooth. You don't want like the interpolation between two shapes going to be crazy. So typically, people will try to encourage a smooth interpolation between the shape. And another reason is probably in the machine learning context, because there are a lot of people are using very large and very deep neural network to train, to solve your problem, basically. And a lot of empirical results shows that using very large machine learning model actually gets you better result. But if you don't have enough data, then you may encounter the problem of overfitting, where your function going crazy between two data points. So in this case, this kind of smoothness measure or smoothness regularization can help you to kind of get rid of this overfitting problem.
Okay, and what are the main challenges here?
Oh, the main challenge is actually I can talk about the challenge I faced during this project. Basically, I come from a graphics background, like doing like a geometry processing and like not involved machine learning at the very beginning. And typically, when we want to do some geometry processing and we want to measure smoothness, we usually will measure, for example, if you have a function and you can take the gradient, you can look at the slope of this function. And a very classic way of measuring smoothness is to, let's say, for example, you take the square of the slope. If the slope is very large, then the function is not smooth. If the slope is very small, then your function is smooth. This is like a very classic way of like measuring smoothness in geometry processing. And the most difficult thing is that if we want to incorporate this knowledge to train a machine model and to make it smooth, this is actually something that's very difficult to achieve, at least in my personal experience. Because in order to, for example, you can imagine a 1D function and you want to measure like the slope, you have to query say, okay, I want to look at the slope at, for example, x equals to 1. I want to look at the slope at x equals 2. And you need to sample many x in order to get many slopes. And you want to make sure all the slopes are going to be small. But in the context of neural networks, this requires very large amount of sample points in your neural network space. And this is actually intractable because basically your trained data, let's say your trained data always lies in x between 0 and 1, and you sample many points between there. And there's no guarantee that your function will be smooth beyond, for example, x equals to 1. So the biggest challenge is that when I try to implement a bunch of a smoothness measure in geometry processing to the neural network setup, they do not work very well. Basically, can't generalize beyond the trained data. So what we end up using is basically a measure called the Lipschitz constant, which we can talk about it later, is that we basically focus on a measure that can generalize across all the input data. We put no assumption on what's the range of the input. We basically try to encourage the neural network to be smooth everywhere without sampling the input space, basically.
Yeah, this brings us right into the contribution. So what is the main contribution of this paper?
Yeah, so as we mentioned, that we focus on something called the Lipschitz constant. And just for people who may not familiar with this concept, this Lipschitz constant is nothing but like the maximum bound of your magnitude of the slope. For example, if you have a 1D function, you can measure the slope, and if you take a slope and then measure the magnitude of the slope and the maximum value of all the possible slopes in this function is called the Lipschitz bound. And people typically assign Lipschitz constant to represent like how large the bound is. And the beauty of this work is that we actually notice that actually not what we observe. Actually, it's very well known in the machine learning community that the Lipschitz constant is something that can be analyzed by looking at the weights of the network. So you don't need any input. Just by looking at the weights, you can kind of measure what would be what's the upper bound of the Lipschitz constant of the network. And the key idea of our approach is basically propose a way to penalize Lipschitz constant, which equivalents to make sure this neural network function is going to be smooth. So the one of the key contribution is to propose a Lipschitz regularization to encourage the Lipschitz constant to be small, which encourages the network to be smooth. And the second contribution is a small architectural change to the neural network so that you can actually effectively make this network aware of this low Lipschitz constant base. So the contribution basically are two. One's the Lipschitz regularization, and the second term is a small change in the architecture to incorporate the Lipschitz constant.
Okay, so before we dive in deeper, let's talk a little bit about related works. So if you had to name one or two papers or even a blog post that were instrumental in writing this paper, which ones would those be?
I would say there are two lines of work that I will strongly recommend all the listeners or all the audience to take a look. The first part is the research on something called the neural fields. Neural fields is basically like you can think of it as a new terminology to describe some fields, volumetric function, continuous volumetric function parameterized by neural network. So for example, something like deep SDF or occupancy networks, that basically are very important works on how to use neural network to represent shapes. And this representation is called the neural fields. And because this is the main representation we work on, I'll definitely encourage people to take a look at these kind of neural fields work. And the second lines of work that I think that's more relevant to the technical detail of this paper is on the parts about Lipschitz normalization or Lipschitz constant of neural network. And personally, I would strongly encourage you all to take a look at a paper called The Sorting Out Lipschitz Functions, I think. It's by James and Professor Roger Gross from the University of Toronto. And the reason I strongly recommend this paper is because personally, this paper is the paper that got me interested into this topic. And their main contribution is not related to ours specifically because they are proposing a activation function that can control the Lipschitz bound of the network. But there are actually other than this main contribution, they have a lot of very good introductory content about Lipschitz properties about the neural network. Basically, this paper is basically what taught me a lot about knowing about Lipschitz constant of a network and how to compute it and what's the variance and what's the importance of this concept. So I'll definitely encourage you all to take a look at this sorting out Lipschitz functions.
Cool. I'll make sure to check it out myself. I didn't know that one. Okay, now let's dive into the approach. So what is the key idea and innovation of this paper and how did you do it?
So as we mentioned, the key idea is to make sure the Lipschitz constant of the network is smooth. So basically the key invention is that we propose a new regularization. You can think of it as just a new term you can add on top to your loss function. And once you add this new term will basically measure this term basically goes very large. If you have a very large Lipschitz bound in your network, basically this term is large if your function is non-smooth. and this function is very small, if function is smooth, has lower Lipschitz bound. So basically, like the key ingredient is this Lipschitz term that you can take your weight matrices from your multi-layer perceptron, and you can compute this Lipschitz regularization, a Lipschitz term, and then you can add it as a regularization to your loss function, and your method will be smooth. But as I mentioned, this is a term that takes your weight matrices and outputs some value, right? And you also want to incorporate the computed Lipschitz constant back to your architecture. So another small modification you want to do is that when you do simple the forward pass of your network, you need to kind of normalize or scale down your weights according to the Lipschitz constant. So basically combining this regularization term and this weight normalization term, which can be implemented in a few lines of code, then you'll be able to train a neural network with very smooth result.
Okay, so for the novice listener that didn't train DeepSDF or any neural field function, so I think it's important to like establish a baseline, right? So in all of these papers, or most of these papers, the input is like an XYZ coordinate plus a code representing the shape, right? Then you have this MLP that processes this input, and the output is this signed distance function, right? The distance of that point to the surface. Okay. And basically in like the standard case, before your paper existed, these weights inside this MLP could be whatever works, right? You have the reconstruction loss. Sometimes you have additional losses. These weights could get whatever. And now with what you're proposing, what that does, right? It takes those weights, and what does it do to them?
So you take those weights, and you first we introduce additional parameter that's called like Lipschitz constant for now. So we introduce another parameter where you will you can think of as normalizing your weights. Basically, it will scale down some rows in your weight matrix. So basically, there's a constant that makes your weights to be smaller. So that's the first thing we do in this technique. And this, once you make this, and so without going through the details, making the weight smaller will make your neural network function to be smoother. So that's just like measured by the Lipschitz count, the Lipschitz bound. So basically, the first thing we do is that take those weights, we will scale it down to be smaller, and then this Lipschitz per layer Lipschitz constant, when we will have a term that basically take those per layer Lipschitz constant and output a value. If this Lipschitz constant are large, then this value is going to be high, and if these Lipschitz constant are small, then this term will be small, and that's basically a term that measures the smoothness of your function. So
right.
So because if you want to train a network, we define a loss function and want to minimize this loss function, right? So if you want to minimize this loss function, then you will try to encourage all the Lipschitz constant to be small. And if Lipschitz constants are small, then in the normalization, it will make this weights even smaller. So that's basically the way we try to make this neural network smooth, or make this deep SDF smooth, by making the weight smaller.
Right. So this is really interesting, right? So you take the traditional MLP that everybody used, but instead of allowing it to get any solution possible, which is basically what it does, right? It minimizes the loss. It doesn't really matter what those weights are. And now you're saying, no, it matters what those weights are. I want them to provide a solution that is actually smooth. So you're saying, okay, I'm going to limit the maximum value of those weights to be very, very small using this Lipschitz constant, which I'm going to then penalize in the loss, right? So you're guiding those weights to achieve a very smooth solution. That's really cool.
Yeah. I think another thing that I can add to that is because usually when we use neural network, we are usually considering the over-parameterized case, which means that there are many, many sets of weights that can give us, for example, identical solutions. And so basically, this method you can think of as a way to filter out some other combination of weights that are very, very large. And when we prefer the ones that with smaller values in the weight values. And this set with smaller weights usually gives us smoother solutions.
And it's only 4 lines of code.
Yeah. Yeah, we start with definitely not 4 lines of code. We start with something that's very large, even involving some computing gradient and autodiff and everything. But like my personal preference is to start by making it work, and once it's work, but it's complicated, and I will try my best to simplify it to get rid of redundant stuff. And at the end of the day, this could be implemented in 4 lines of code. So that's a part, my favorite part, because everyone can implement it. We even provide the source code in the main text of the code, main text of a paper.
I even implemented it myself. Okay, but let's get back. I guess this kind of starts to drip into the results section, but let me challenge you with the questions. Aren't there any other ways to make the solution smooth as well?
Yes, I think there are a lot of ways that we can make it smooth. And for example, I think the very, very obvious way is probably just borrow, because when I mentioned earlier, there are a lot of Lipschitz normalization work in the machine learning settings. And there are a lot of those papers that what they do, just briefly summarize what they do, is that they will set a bound. They will manually define, say that, okay, I want the Lipschitz constant to be something like 1. And then they constrain the weights to not having Lipschitz constant more than 1. And this, if you use this approach, you can definitely make your solution smooth. But in the context of, for example, what we want to do is shape interpolation, it's very, very hard to actually guess what is the optimal Lipschitz constant. Because if you want to set it to be very, very small, then the neural net is probably too smooth to fit a complex function. But if it's too large, then it is not smooth at all. So one way, if you want to make sure your solution is smooth, you can definitely use this kind of Lipschitz normalization. If you search this term, I believe, or spectral normalization, you will find a lot of papers on it. But this is very hard to control. Basically, personally, I also needed try like many hyperparameters to find out one that works okay, but it still not works optimally compared to the soft version of Lipschitz normalization. And there are also other ways that you can do it. For example, like the old ways, you can penalize the L2 norm of your weights, or I don't know, L1 norm or some other norms of your weights. I forgot the name of that, but basically penalize the L2 norm of your weights. You can also encourage the weight to be smooth. But in my experiment, I found that these kind of method can make the weights small for sure, but it's not necessary making the solution to be smooth measured by our Lipschitz constant. Basically, I think in one of the experiments we tried is that we use this kind of L2 regularization, and then when we can make sure the weight value is small in the under L2 sense, but the Lipschitz bound of the network can still go up, which means that this network can still be non-smooth, even if the summation of the weights are small. So I think there are many ways we can do it, and here are just like 2 examples that is commonly used in machine learning fields.
Okay, so now let's dive into some of the results. So how do you even evaluate the performance of this kind of thing?
Yeah, I think partly it's because we are kind of submitting to the SIGGRAPH. So a majority of our evaluations are very qualitative. Basically, the toy example we try is that we just randomly pick 2 shapes, like a torus and a double torus. And what we do is that we train the deep SDF model to fit a 1 torus. Let's say the latent code to be just a scalar, latent code is 0. And we can say that, okay, we train the same SDF, but when latent code equals to 1, it needs to become a double torus. So we have a same network. When latent code is 0, it's a torus, and latent code is 1, it's a double torus. And we just smoothly change T, like the latent code T from 0 to 1, and we can interpolate this torus to double torus, right? And a basic qualitative example is that we just do this interpolation to see what the result look like. And we can see a lot of figures in the paper that if we use Lipschitz regularization, the interpolation is going to be smooth. So like that's one kind of qualitative visualization, but we also try a lot of other quantitative things. For example, we can use standard way of measuring smoothness that I mentioned very beginning. Like we can take the slope of the function and take the square of that slope, and we can measure the value of that slope, right? And we can also, so we basically train like under a traditional setup and our Lipschitz setup. And then we can use this standard way of measuring smoothness to compute a value. And basically, this also shows that our method can encourage smooth solutions. So yeah, and there are also other experiments. For example, we also try another application, which is called a test time optimization, which is, I think is very popular in terms of like in the reconstruction field where because we remember that the deep SDF, we take a coordinates and the codes of the shape and output some sign distance function of the shape, right? And basically different codes represent different shapes. And so in a lot of reconstruction paper, they will try to do the optimization on the code. So after your training, your network is fixed, but they want to figure out what's the optimal code so that it, for example, better reconstruct a point cloud. But usually if your network is not smooth, and this optimization or figuring out the best latent code will usually be something that's not what you will expect, because the kind of the network function can go crazy, and those crazy function may luckily be a very good fit for your point cloud and it will stop here. But if your code, your network is smooth, and the move from latent code is also going to be smooth, it will usually give you a better result if you do this kind of a code optimization.
Yeah. So this is you're talking about the auto decoder kind of setup. Yeah. So if the space is not smooth, you may end up at a point that's right between two shapes that were in the training set, and that's basically nothing there, even though that minimizes the loss on the input point clouds. But what you actually want it to be is the actual shape that it represents, which is a really challenging task. And this is one of the really nice results in the paper. Another nice result that I personally really liked is how you showed, like in the 2D case, how when you use your Lipschitz MLP constraints, then you get between two shapes, you get this very almost linear, I want to say, change in the shape. While if you don't use it, then everything is kind of squished down to the first, about a third of the way between them. That was a really nice result to show.
Yeah, I think that's basically the outcome of using traditional measure, where we only choose a bunch of sample points and then penalize the slope. But on the region we don't have samples, the network can go crazy. The network is very, very powerful in terms of fitting something crazy, even in a small region of the input. So I think that's the reason why traditional measure may not be that suitable for getting smooth solution.
Yeah, you had another interesting experiment where you were looking at adversarial attacks.
Mm-hmm. Oh, yeah. Oh, this is actually tied to another class of related work, because actually the reason why Lipschitz network is very popular in machine learning field is because in machine learning, there's a concept called the adversarial examples. So just a brief background for people who first time hearing this word is that let's say if I train a very, very powerful image classifier on, a large image data set, and if I give you monkey will output 99% monkey, if I give you a dog, you will output 90% is a dog. So it will very, very good image classifier. But it is very well known that if you use this kind of state-of-the-art image classifier, it will suffer from an effect called adversarial examples. Basically, if I give you, the famous example, if I give you a panda, and the network will tell you it's 89% is a panda, for example. But if I add a little bit of noise to this image, where the noise is so small that the human eyes can't tell the difference, but this noise may trigger the machine learning model to have very crazy misclassification. For example, turning a panda into, something else like a dinosaur or something. And so basically, this effect that a state-of-the-art network is vulnerable to this kind of very, very tiny perturbation has a lot of security implications, because it indicates that even if some noise in the image, it may trigger crazy misclassification. This is not a very good thing if you really want to deploy machine learning model to real world. And the use case of Lipschitz constant here is that actually there are a lot of research study how to make this kind of large model robust to this kind of perturbations. And one of the results show that making sure the network has small Lipschitz constant is actually very useful to be robust to this kind of perturbation. So in this work, we just try to kind of demonstrate our case can encourage small Lipschitz constant, and then by showing kind of reinvent the wheel, or not necessarily reinvent the wheel, but basically verify other people doing the research about showing small Lipschitz constant is robust network. And we also show the same thing that if we train a network with smooth MLP with small Lipschitz constant, we can also be robust to this kind of adversarial perturbations.
Yeah, that's a really nice application to show where these kind of smooth solutions are also beneficial, not only just for the visualization and graphics kind of applications, but also in this robustness to adversarial attacks. So, in which cases does the method fail? Can it fail? Does it have failure modes?
Yeah. Yes. I think there are. It actually contradict to another popular line of work in machine learning field, which is called like the positional encoding, or a lot of those like sine or cosine activation function. Because so just a little bit background is that typically in the deep SDF we may input like XYZ coordinate to the network, and there are a lot of people discover that if you, instead of inputting X, for example, X coordinate to the network, you input sine X and sine 2X, sine 30X, basically having some periodic function with high frequency times this coordinate. Basically, this is called like the positional encoding or frequency encoding. There are many names for that. And if you add this kind of things, it can encourage the network to learn high frequency functions, basically try to learn something that's very high frequency and non-smooth. And we actually try that if we use this positional encoding and without Lipschitz regularization, we will not be able to get a smooth solution. And that is because when you want to do this kind of positional encoding, you already want the network to learn something that's high frequency, which is kind of completely opposite to getting a smooth solution. So I think in this case, simply using our Lipschitz regularization will not give you a smooth solution. But I can tell you, if you think deeper, you will be able to figure out like an architectural change that can still use positional encoding, but make sure the change in the latent code to be smooth.
Yeah, so this actually brings me to the question of, there's like, so you used the traditional ReLU activation or soft class activation based networks, but there's this new line of work of sirens, right? The sinusoidal activation based networks. So what you're saying is that this regularization will not work for sirens out of the box?
It will not. This will not work first, because those siren thing, I just think it's more like you are doing something in the frequency space. But even like, if you think about like the do Fourier transform and look at those frequency values, even the frequency values look the same, but there are some, but the high frequency component, the small difference will change a lot. I would say if you use this kind of siren, this type of approach, because you're already working on like high frequency domain. So even if your function is smooth kind of in the frequency domain, it doesn't mean that it's smooth in the spatial domain. So I would say like, if we really want to use siren, but still want to use the Lipschitz thing to encourage, for example, the interpolation to be smooth, like one possible idea is you can have, for example, like two branches of your network. There's one taking those XYZ coordinate and map some function, and the other network, for example, take the latent codes and map to something, and then you can merge them together in some way. In this way, that you can make sure that your change in the latent code will not result in abrupt change, because like the latent code network is kind of Lipschitz smooth, but you can still leave the siren network there to do what they want to do, like basically learning some high frequency features.
Yeah, so like kind of changing the architecture to disentangle between the latent code and the spatial coordinates. And this way you still maintain the smoothness in the latent space, but then you allow the frequency space to be as crazy as it needs to be. Very interesting.
Yeah.
Did you get any unexpected findings, any unexpected results?
Yeah, I think there are I would say one detail that bothers me a lot when doing this project, because back then when we just train this kind of MLP with the L2 regularization and then without Lipschitz regularization, actually, if you just train it, you can make sure these two things are as I mentioned earlier, they will both encourage the weight to be very, very small. And I think one unexpected finding is that back then I just said, okay, are we inventing something useless because they both can make the weight small? Then what's the difference? But actually, when I stuck on that and I do more experiment on that, I actually noticed the conclusion I mentioned earlier is that even if your weight small, the Lipschitz concept of network can still be large. It means that the network function can still be not very smooth. So we actually notice that like the key difference of this compared to those traditional regularizations that we penalize the thing we want to penalize. We penalize the smoothness of the network instead of just making sure the weight is small, but it is unclear what's the relationship between a smaller weight and a smoother function, because no one can tell you that like a smaller weights in terms, especially the summation, is small, can guarantee you smoothness. You can still have, for example, if I have, I don't know, the weight, let's say the weight's just as ABC, 3 values, you can, if you say like the summation is 10, you could be like 0, 0, 10, you could be like, 3, 3, 4, a 3, 3, 4 function is going to be smoother than like a value with like very big weights. So yeah, I think there are a lot of interesting findings there, but this is one of them.
Yeah, interesting. Okay, moving on to the next section of the paper, conclusion and future work. So how do you see the impact of the paper going forward? And if you know of any interesting papers that followed it or future interesting projects, things that are left open, please share.
Yeah, I would say I personally, I'm very excited about this kind of smoothness measure, because you can know that like a smooth measure are like how useful a smoothness measure is to a lot of, especially graphics applications, like not necessarily like shape interpolation we show, but there are also a lot of other things. For example, if you want to transfer function from one shape to another, you want the transfer map to be smooth. And I know in reconstruction, if you have some missing region, you also want this region to be smooth. I think there are many applications that wants a solution to be smooth. And we only explore a few of them, but I'm very excited to see like how this kind of smoothness measure can be used in other applications. And beyond like graphics, I'm also interested in seeing like more MLP based application, because MLP are basically used everywhere, not necessarily in machine learning, in graphics, but I know in other medical fields or in vision, and like everyone's using MLP. And I believe this is like just a general smoothness measure for MLP. So even if application beyond graphics, I'm also interested to see how they would happen. And another follow-up that's interesting, and you also briefly mentioned earlier, is that the interpolation we get is more like a linear interpolation between the two shapes. But interpolation, there's already a lot of great papers showing that if you're doing optimal transport, or another term is called Wasserstein distance, and this will give you like more I would say more reasonable or more visually appealing interpolation between two things, not just linear interpolation. And because it's actually aware the true distance of transporting a pile of mass to another pile of mass. So I'm also interested in current smoothness, for example, in the space of optimal transport. I think that's also another thing that I'm very interested in.
Cool. Okay. Yeah, it's super interesting, this future work direction. Any early career PhD students looking for your next project? Here you go. Okay. On to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments that the reviewers had that made the paper better.
Yeah, actually, I was very lucky with this project that the reviewer 2, usually, which is the most negative one, does not give us a lot of like negative feedback on that. I think most of the reviewers appreciate the simplicity of the paper. They really like the fact that this could be implemented in like only a few lines of code. And they also love the evaluation we did in the paper by inventing, 4, 5, 6 different baselines and then compare against them. I think they really like that we do like evaluation in terms comparing with a bunch of alternative techniques and the simplicity of the code. And most of the negative feedback is mainly about having more results. For example, I remember the first time we submitted, we only have a couple 3D interpolation results, but I think right now there are more results in the appendix, and that's thanks to the reviewer suggestion on showing more results. I think previously we were kind of limited by the page limit, so we didn't include so many results, but I think reviewer does a great job of suggesting us to put, I think, 2 or 3 more pages of result in the appendix. So right now the paper is more fun to read because you have more results to check out.
Yeah, I totally understand where the reviewer is coming from. In this fast-paced field, there's the fear of, is this cherry picking or is it actually working, right? And the fact that you can provide more results basically answers that question. Well, no, it's not cherry picking. Use whatever two shapes you want and you get and it's smooth. And yeah, that definitely made the paper better. In my opinion, like for me, reading it, I was just looking, I want another example, and they're all so satisfying to look at. And you see the smoothness compared to, the traditional one without the Lipschitz constraint. It looks really nice.
Thank you. Thank you for the kind words.
Okay, it's time to wrap up. So, Derek, thank you very much for being a part of this podcast. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.